Okay, today we're going to talk about the sums and differences, or I guess I should have put an S in there, sums and differences of functions. The group that had this probably realized that this is a fairly straightforward one. I think it's actually very similar to many of the topics in this section. You know, if you did the product, you'll see some similarities here. If you did the quotient, you'll see some similarities. Only groups that won't see some similarities is the group that did the function composition, and those of you that did the equations and the applications. So I've written here f plus or minus g at x. I could have written one with a plus and one with a minus, but I figured that you guys could figure out that we're either talking about a plus sign in the bracket here or a minus sign, not both at the same time. The rules are the same, so I figured rather than writing it out twice, we would just write it once. So this is the way that we read this is f plus g at x, and really, or f minus g at x. The way that you write that, or another way for you to understand that, is that that's just equal to whatever f at x is plus or minus g at x. And that's basically what this section's all about, is taking two different functions, sticking a plus or a minus sign in between them, and going from there. What it means in this case is for any given x value, if we want to find the y value of our new function, f plus g or f minus g of x, we just add or subtract the y values of x and the y values of, the y values of f and the y values of g. So take the two y values, add or subtract them accordingly, and whatever answer you get is the y value that goes with f plus g of x. And we'll do an example so you can see what that looks like. We can certainly do this with a table of values, so you can make a table of values. The table would look a little bit different than the one that you're used to seeing. You could have an x in it. That's not an x. You can have, instead of a y, you can have f at x and g of x, because you have two different y values. So if the y value at 0 was 3, the y value at, the y value for g at 0 was 5, then f plus g of x would have a y value of 8. And that just comes from adding 3 and 5. Does that make sense? I mean, obviously, I think you guys know that 3 plus 5 is 8, but now we're talking about not just adding numbers, we're talking about adding functions. So and I'll show you how to do it graphically. Say that again? Yeah, I mean, you can add those. Yeah, for sure. I mean, we'll do an easier one, but certainly these can get as complex as anything else or any of the other functions that we've looked at.
Would it be log x plus sine x?
Yep.
Or would it be log plus sine?
Nope.
X?
It would be log x plus sine x. And we're going to do an example so you can see that. Where? Here?
Yeah.
Yeah, so this is kind of the notation. So f plus g of x, it just means take f at x and add g of x to that. So this is kind of like a compact way on the left here, compact way to write all of this out. They obviously mean the same thing. You can write one instead of the other. It doesn't really make a difference. Is that okay? Everybody done with that? Let's do an example. So here are two functions, f of x and g of x. F at x is negative x squared plus 3. G of x is negative 2x. And if we're going to write the function f plus g of x, should have left maybe a little bit more room in here. It's just equal to f at x plus g of x. So we can just write these out. Negative x squared plus 3 plus, there's a negative 2x in there, So algebraically, we can add the two functions together. No, because it's addition, right? So the sign shouldn't change if we're adding.
If it was minus,
yeah, and that's what we're going to do next. So the next one will be a subtraction. So similarly, f minus g at x is f at x minus g at x. And as John said, here's where we get a change in sign because we're subtracting. Really important here, our g of x was just a single term, but had g of x been a trinomial with three-termed expression, really important that you get the brackets in there so that this, the minus sign gets distributed. And I guess we can simplify this a little bit, clean it up. So from a strictly algebraic point of view, that's all that's involved with adding or subtracting these functions. Obviously, if there are like terms, if we took two quadratic functions that had quadratic terms, linear terms, and constant terms, and we were going to add them together, we would make sure that we collect all the like terms so that it was as simple as possible. That's the algebraic way of doing this. We can do this with equations. We can do it with a table of values, kind of like we did on the previous page, where we list the x values, we list the y values, and then we just add the two y values to get the y values of the new function. And the last way that we could do this, sorry, I thought this was big enough, but it's clearly not, is graphically. So if we're going to do this graphically, what f plus g of x means is it means take these two functions and add them together. So for any x value, let's say right here, take the y value of the linear function and add it to the y value of the quadratic function. Well, here, the y at x equals -1, the y value for the one function is 2. The y value for the other function is also 2. So when we add those together, we're going to get a value of 4. Is that okay? Just take the two y values, add them together, and you get your new y value. And you can do that, anywhere along the graph. I maybe should have kept a little bit more of this graph. Anywhere along this graph, you can kind of just take the the y values and add them together. And if you do that in enough places, you'll have a good idea of what this function looks like. This one was fairly straightforward. It's a quadratic. We could find out what this looks like either by factoring or completing the square or whatever the case may be. Or we can just kind of go through the process of taking a few points and adding them in. What happens here? What happens when we add this point here and this point here? Why is it the same? Right, so the other day, some of you were asking me, when you combine these functions, how do you know which one to use? Sometimes it's useful to look at the characteristics of one function, and that will help you determine the characteristics of sort of the new function. In this case, at any of the zeros, when we add the other function, we shouldn't get a change in value. What about, we're going to do this on Monday, but just since we're here, what would happen if instead of adding these two functions, we decided to multiply these two functions right here at x equals 0? How come it would be 0? Sure, 0 times anything else. So that's a clue for those functions that we had the other day where you had some graphs and you had some equations and you kind of had to see. It's helpful sometimes to look at the zeros of the function, the original functions, and see where the sort of combined functions, what might happen there to help you determine something. So it's kind of like a clue, I guess, about what's going on. Going back to this, yeah, sorry.
So if you're graphing it, you just add the x values together?
No, you keep the x values the same. and you add the y values. So for instance, if we want to know the y value here at x equals 0, we take the two y values and add them together. So here the x value is, sorry, the y value is 0. Here the y value is 3. 0 plus 3 is 3. Is that okay? We could probably do it over here as well. I'm just trying to see where else we can do this. I feel like something kind of went wrong in here, given that this was 4. This is okay so far, but as I look over here, let's have a look here. What's the y value here and the y value over here? 0. It's -2, +2, so the y value would be 0. I guess we're okay. And then we could probably go, maybe, I'm just trying to find another point. That I guess these points would be easy enough to add. So it's -1. Whoops, sorry, I got the wrong one. Oh, no, that's right. So we have -1 here and -4, so the y value at x equals 2 would be -5. So this graph is looking like it's going to go like this. And I didn't really include enough information over here, but any guesses as to what's going to happen to the left here? Yeah, why do you think it's going to come back down? How do you know it's a parabola? I guess, okay, so the equation that we found earlier was a parabola, so that's good. Just looking at this graph, if I didn't tell you that the final result was a parabola, how do you know that this graph is going to go back down? This one's linear, so the blue one's linear, but notice that the linear one is growing much slower than this one is decreasing, right? So this is going to kind of take over. The negative, these values get much bigger. In fact, what's the y value here? It's -6, and the y value up here probably isn't going to be quite 6, right? So we know we're going to have some value that's kind of decreasing. So we're going to get a graph that looks something like this. So that's how we can do it graphically, is just remember the vertical line test. That's kind of what we're doing here. We're not doing a test, but we're drawing in vertical lines, and we're taking the result where each of those functions are, and in this case, adding them together. If instead of finding f plus g of x, if we wanted to find f minus g of x, we would do the exact same thing, except instead of adding the two y values, we would subtract them. Yeah, so good question. If the question looks like this, if it's an f minus g of x, then we subtract the g from the f. But if the question is like this, then we would go the other way. And it's important to know that these are not equivalent, right? These two things are not equivalent. They're going to give you different results because of that minus sign. And obviously, when you do subtraction, the order becomes important. So. The flip side of that, though, is that f plus g at x and f and g plus f will be the same thing. How are these going to be different? That's a good question, John. We've done this one already, right? Let's do this one. So this one says take g of x and subtract f at x. Thank you. And then f at x, I've kind of lost. It was this here, right? -x squared. You got it? So this is not the same as this one up here.
Not the numbers.
Sure, the numbers aren't going to, well, in this case, they are because we didn't have multiple squared terms and multiple linear terms, but yeah. Any questions about how to do that? So we've looked at algebraically, we've looked at graphically, we've talked about the table a little bit. The only other thing that you need to know for adding and subtracting these things is about the domain and the range. Not so much the range, but the domain. Oh. So the domain of f plus g at x or f minus g at x is the intersection of the domains of f and g. Those of you that took data management, that intersection, when we talk about sets, is this little symbol here, as you might remember it, upside down U. Did you take data management? Yeah. What that means, the intersection just means what they have in common. You can think of it as a Venn diagram. If this is the domain of F and this is the domain of G, this is the intersection. This is what they have in common. Or if you want to, you can think of it kind of like a number line. Oh, let me change colors here. And you could say, well, F is, let's say that F is like a linear function and it's defined everywhere. But G is only defined from here on over. Well, that was funny. Let's try that again. Then the combined function here of adding F and G together would only be the parts that they share, only the parts that overlap. And we'll do an example again so you can see concretely what's going on. So in this case, we have an exponential function and a logarithmic function. I'm just going to move this out of the way so I can draw some more. I'll let you guys catch up. Again, if I asked you to find F plus G at X, you would just add those two functions together. So the combined function would be 10 to the X equals log of X plus 5. Looks like I have an extra bracket there on the end. That one you couldn't simplify anymore. You would just leave it as it is. Because we're dealing with two functions here, I'm going to put the domain of F and the domain of G. What's the domain of 10 to the X? Exponential function. Are there any restrictions on X? So would one work? Can we sub in 1 for X? 10 to the 1?
Yeah.
That's possible. 10 to the 0?
Oh, I'm sorry.
That works. 10 to the negative 1? What's 10 to the negative 1? 1 over 10, yeah, okay. So it's kind of looking like here the domain of X is anything. So X is an element of the reals. No restrictions there.
Wait, why is it 1 over 10?
Because you flip it so it's positive from the 1 to the bottom.
10 to the negative 1 is the same as 1 over 10 to the 1. Exponent becomes positive. I just can't seem to get a decent looking G over here. What about the domain of G? The log of X plus 5. We probably shouldn't talk about this too much given that one's doing his test. I wasn't thinking too much. Just negative 5? Anything less. So the domain here is that X has to be greater than or equal to negative 5? It can't be equal, sorry. X has to be strictly greater than negative 5. So if we were to look at that on a number line, we've said that, so here's the domain of F, and here's the domain of G. Yeah, so here's the domain of G. Their overlap is this little bit right here. So the domain of the combined function, so the domain of F plus G at X is going to be that X is an element of the reals such that X has to be greater than negative 5. Now there's no, is that okay? The idea of the overlap, whatever they have in common. In this case, it was kind of, whatever they had in common was just the domain of G, but there could be some restrictions on the domain of F and the restrictions on the domain of G, which would actually cause a further kind of reduction in the values that you had available. Then you have to exclude that as well. Yeah. So anytime one of the functions is undefined, then you have to exclude that from the combination. And it kind of makes sense, right? If you were trying to add two values, and one of the values was non-existent because there was a hole there. You can't just say it's 0 because that's quite different from being non-existent. So your combined function would not exist where that hole was either. Same with the vertical asymptote. Combined function couldn't exist.
We know there's a hole that's like X is an element real, it has to be like greater than 5 and less than X. Like, you know when there's like a break between the two?
Right.
Notation?
Yeah.
How you know there's a hole?
Yep. There's no special, I mean, so we talked here about how to define the domain of a function. You kind of look at the overlap. There's no special way to deal with the range. What we have to do is we kind of just have to plug in some values. We've restricted the domain, and we've said that the domain for the domain x has to be greater than -5. So let's look at what happens when x is either at -5 or really close to -5, because obviously there's something that happens there. And let's look at what happens as x gets really large. I don't know what this function f plus g at x looks like. We could write it out here. But really what I want to know is what's happening around -5. Because that's probably going to create, wherever we have some restrictions in domain, we're probably going to have some kind of restriction in the range as well. So let's have a look at, we can't sub -5 in here, but can we substitute like something close to -5? Sure, -4.9. Without even going to your calculator, -4.9 plus 5 is going to be, it's funny because in my head, I made the same mistake that you did. And then I realized it was a mistake, and you said the same thing. And I thought, oh, wait a minute. So yeah, so this will be -4.9 plus 5 will be 0.1. What's the log of 0.1? So the log really, really close to 0. Negative, a big positive, a negative. Like, remember the log function looks like this? So at 0.1, we're looking at a big negative. Plus 10 to the 0.1. What's 10 to the 0.1 going to look like?
No, 10 to the 4.9.
Oh, sorry. Yeah, sorry. 10 to the -4.9. So it's so it's pretty small, right? So this number is going to be negative, but the closer we get to 0 in this direction, the closer we're going to get to, or sorry, the bigger we're going to get in the negative direction. So it looks like we could certainly go to -infinity. And this graph, as x gets really, really, really big, 10 to the 100 is a huge number, right? So even though we've restricted the domain, it looks like the range will go on forever. So it looks like the range here is going to be that y is an element of the reals. And we can do a little graph and have a look at what it looks like. And I think oh, maybe let's have a look. If you want to do some work to check your work in Desmos, just a couple of points. It's easy if you call your function f at x and g of x, and we can just do the combined function at the end, and you don't have to type the whole function over again. Oh, sure. Yeah, you want to get all fancy. What did we say here? X minus 5, right? Right. Leslie, to answer your question about why not just put them together, I wanted to put them together so you can see them individually. And what do we do? We're doing f plus g plus. Is that what we decided? So you can see, ooh, fancy, that the range is in fact all real numbers. It goes forever in the negative direction, forever in the positive direction. Any questions about adding or subtracting functions? That's basically it. All right, if there aren't any questions, your homework is right up on the board there, page 528. I'll write it here as well. Oh, this is tomorrow's work. Sorry. Yeah. No. You can think.